Hi, this is Mrs. Kidman, and in this video, we are going to be discussing properties of parallelograms. So when we talk about a parallelogram, it's defined as a quadrilateral. So it's a type of quadrilateral, or it has four sides. So a quadrilateral where the opposite sides are parallel. So and oftentimes when we think of a parallelogram, we often see something like this, where the opposite sides here are parallel. Now, because these opposite sides are parallel, we actually can learn some really cool things about parallelograms. Because they're parallel on opposite sides, we also know that opposite sides are congruent, opposite angles are congruent, their consecutive angles add up to 180, and that the diagonals bisect one another. Now, in this video, I am going to go over a brief proof of each of these things so that we know that just based on this idea of knowing that they're parallel, we can actually use some of those parallel line cut by transversals theorems that we've talked about in previous videos to then prove that each of these things are true. Now, once those are true, we are going to use these things to then find different parts of quadrilaterals. But really what we care about here is what are some of those properties and why do they work? So let's first start by taking a look at why parallelograms have opposite sides that are congruent. So just to start, what we're going to do here is now this proof here, as a heads up, is going to be kind of an informal proof. What that means is I'm not going to write out a two-column proof or necessarily a paragraph proof, but I'm going to explain it verbally while adding in pictures just to help us understand what's happening. So the very first thing I want to do here is I actually want to construct a line that goes through Q and S. Now the reason why we can do that here is because the definition of a line is the shortest distance between 2 points. So a line actually exists between any 2 points. Now, by the definition of parallel, we know, or parallelogram, we know that this side is parallel to this side, and we also know that this side is parallel to this side. Now, note that notation for parallel there, and that's just because this is a parallelogram. That's what it means to be a parallelogram. So that means that this QS here acts like a transversal for these lines. This line QR, and this line PS. And so based on that being a transversal, what we know is that this angle PQS is actually going to be congruent to angle RSQ. And the reason why is by that alternate interior angles congruence theorem. So we know the alternate interior angles are congruent. Well, these two angles here are actually congruent because it's cut by that. We also know the angle PSQ, so I'm going to label this one in blue here, that this angle is congruent to this angle by the same property, that they're alternate interior angles. Now, notice how those two angles are congruent and those two angles are congruent. Similarly, I know that this side in the middle here is actually congruent to itself. The reason why we know that is by that reflexive property. Anything is congruent to itself. Similar, we can also use the symmetric property. It depends on how we're defining it. So what I'm saying is by the reflexive property, QS is the same as SQ. Now I want you to notice here, I can go this black angle, the purple line, and blue angle, and the black angle, the purple line, and the blue angle. Notice how that diagonal actually split this up into two congruent triangles, or two triangles, and we have just proven that they're congruent. So by angle side angle, we know that triangle PQS, or this triangle here, is congruent to triangle RSQ, right? So those two triangles are congruent by angle side angle because we using that alternate interior angles theorem and the symmetric or reflexive property, depending on how you want to define it, we know that by angle side angle, those two triangles are congruent. And what do we know about congruent triangles? Well, by corresponding parts of congruent triangles being congruent. So by that theorem that say corresponding parts of congruent triangles are congruent, we then know that PQ has to be congruent to RS and QR has to be congruent to SP. Right? Sorry, I don't know what is up with these signs. Equal to congruent. Awesome. So that is how we would show that when we're given a parallelogram, the opposite sides are congruent to each other. And that is actually called the parallelogram opposite side theorem. Now let's go ahead and look at a proof where we demonstrate that the interior angles of a parallelogram, or those opposite angles, are actually congruent to each other. So just like we did before, we actually want to construct a diagonal from B to D. And that by diagonal, we're Now that one is not very straight here. Now our diagonal, again, is going to act like a transversal. And the reason why it can act as a transversal is, remember that by the definition of a parallelogram, I know that this is congruent to this, and these are congruent to this side, right? That's by the definition of a parallelogram. So with that being said, we can then use that alternate interior angles theorem, just like we did before, to say the angles are congruent. So I know that this angle is the same as this angle. Similarly, I know that this angle is the same as this angle. And because those angles are the same and this side is the same as this side, just like we did it in that last problem, we know that these two triangles are congruent to each other. And that's by that angle side angle theorem again. We know that triangle ABD is congruent to triangle CDB. Right? Now, because we know that those are congruent based on those things, we actually know that this angle here, sorry, some of that purple can be a little distracting there. Let's get rid of that. So because those two triangles there are congruent, we actually know that that means that this angle here, or angle A, is going to be congruent to angle C by that corresponding parts of congruent triangles. So that tells us that these two angles are congruent to each other. Now, how can we prove that angle B is the same as angle D? Well, what we actually want to do here is we want to break down those angles. So I know that angle B is equal to angle ABD plus angle, or the measure of this angle, measure of angle ABD and angle DBC. We also know that the measure of angle D is equal to the measure of angle CBD plus the measure of angle CB, or not CBD, ooh, that one's wrong, CD. So we're looking at this angle CDB and ADB. Now, we established earlier that these angles are the same and these angles are the same. So what I'm going to do is I'm actually going to replace these. So that means that the measure of angle D is actually equal to the same thing as B, measure of angle ABD plus the measure of angle DBC. Now, again, that's by substitution, because we know by that alternate interior angles theorem, that those two things are equivalent to one another, right? So when we know that those are equivalent to one another, which is awesome, we can actually substitute that in. And so we end up getting that the measure of angle B equals the measure of angle D, and that's just by the transitive property, right? So if B equals this and this equals D, then by the transitive property, we know that they're equal to each other, and we don't care about proving that they're equal, but we want to show that they're congruent, and we know that equal angles are congruent angles by the definition of congruent angles. So that's how we can kind of prove that. Again, using those congruent triangles, using that angle addition postulate, which says that I can add two angles that don't overlap and make it the same full angle. So that's how we show that those are the same. Running quickly through some of our other proofs here, to prove that adjacent angles are not parallel, but they actually add to 180. This is a really cool thing that we have with parallelograms. The reason why they add to 180 is, imagine this one acting as a transversal here to this, and these two angles here are same side interior angles. And because they are same side interior angles, that means that angle A plus angle B equal 180. Now, we don't know that they're the same, so I'm going to label them as X and Y. And through substitution, that means that X plus Y equals 180. So that's kind of a very simplified proof of why that works out, but that is a really important thing to keep in mind. So as you're trying to figure out different angles, we can use this property here. Now, the very last one that we're going to talk about when it comes to a proof here is going to be, why are the diagonals bisectors of one another? And this proof is kind of an interesting proof here. So again, based on that definition of parallelogram, we know that these are parallel, that QR is parallel to PS. We also know that PQ is parallel to SR. And so that's important to know. And because those are parallel, each of those lines acts as a transversal So PQ acts as a transversal of QR and PS. RS acts as a transversal. QR can act as a transversal of those two. So basically what that means is that this angle QPR right here is going to be the same as angle SRP. And we also know that PQS, so this angle here, is going to be the same as angle RSQ, because all of those are considered alternate interior angles based on the line that we defined as our transversal. So for these two with the double lines, our QS is defined as a transversal. For this one, we have PR, which we define as a transversal. And remember, we can always draw another line in there because a line is just the shortest distance between 2 points, and lines always exist between 2 points. So based on knowing those two angles, we also know that this side is the same as this side, and we actually know that PQ is congruent to RS based on that opposite sides are congruent theorem that we already proved earlier in this video. Okay, so using that, we know that those are the same. And so then again, by angle side angle, we can prove that triangle MQP is congruent to triangle MSR. And because those are congruent by corresponding parts of congruent triangles being congruent, by that theorem, we know that that means that PM is congruent to MR, and we know that MQ is congruent to MS. And because they're congruent, that means that they're the same length. So PM, so those segments are congruent, which means PM equals MR, and MQ equals MS, meaning that M is the bisector of PR and QR based on the definition of a bisector. So now these 4 proofs that we've gone over have been very informal. We've kind of walked through them. We haven't written up a 2-column proof, but really I just wanted to show you, why does this work? Why is it okay for these things to be said? Now, what we've shown in this video is these 5 things. This is either given or can be proven based on the definition of parallelogram. But remember, a parallelogram is a quadrilateral that has the following properties contained within it. The opposite sides are parallel, the opposite sides are congruent, the opposite angles are congruent, the consecutive angles add up to 180 degrees, and the diagonals bisect one another. So using these properties that we know about parallelograms, let's just go through a couple of examples here of how we can decide things that we know. Now, I want to find each of the indicated variables here. So I know that this piece and this piece are the same. Why do I know that? Because opposite sides of a parallelogram are congruent. So 7 equals 16 minus h. Well, 16 minus h equals 7. So we can figure out what h is by subtracting 16 from both sides, and we get -9 equals -h, or h equals 9. To figure out g, remember that by that, and that's by that opposite sides theorem. Using the opposites angle theorem, we know that this angle is the same as this angle, so we can set those equal to each other. 65 equals g plus 4, and we can solve for g by subtracting 4 from both sides and get 61 degrees is what g is. Now let's take a look at this next one over here, or this next one down here. So we want to figure out, these next two both deal with angles. Now, knowing those angles really help us knowing some of those relationships. So what do we know about the relationships here? Well, I know that this angle is the same as this angle, and this one is the same as this one. I also know that this one plus this one equals 180. So to figure out what those angles are going to be, I can actually just do, to figure out what n is, I can actually just do 180 equals 95 plus the measure of angle n. And then we can do that simple math to figure out what the measure of angle n is. And in this case, the measure of angle n is going to be 85 degrees. Okay, and that is using that theorem that says that the adjacent angles of a parallelogram add up to 180 degrees. Now this last one is kind of the kicker. We need to figure out what these all are. Now we know a couple of special things about these. I know that b minus 10 plus b plus 10 plus c plus d equals 360, right? We figured that out when we learned about angles and polygons. We also know that d is the same as this, and this is the same as this, and these two add up to 180. So using all of that information, we also can figure out b because we know that these two add up to 180. So that's where I'm going to start. So b minus 10 plus b plus 10 equals 180. Well, our 10s cancel, so 2b equal 180 degrees, and that means that b equals 90. So if b equals 90, this angle here is 80, this angle here is 100. We know these two are the same, so d has to be 100 and c has to be 80. Notice how they only gave us variables here with a little bit of numbers, and we could use those to find the interior angles of the whole parallelogram. How cool is that? So again, parallelograms are quadrilaterals with some really special properties. In this case, those properties are the ones as follows. So if you have any questions, feel free to check out more videos or reach out to me. But these are properties of parallelograms and kind of a proof on why they work and why that is so cool that we have them and what we can use them for.